let's talk about factorial ANOVA. So, if you understood the material from the last class, this should not be that hard. If you are confused about the stuff from the last class, this is going to be really hard, probably. So if you are not confused, or if you're not confused, you're good to go. If you are confused, after this class, like watch the video for the last class. Because this class is based off of the last class, but it notches things up. Not just like one level of complexity, but like several levels of complexity. And for the next class, when we talk about repeated measures ANOVAs, we'll be doing repeated measures factorial ANOVAs, and that again will kick the complexity up quite a bit. So, before next class, you want to make sure that you are reasonably familiar with the one-way ANOVAs that we did last class, and then the factorial ANOVAs for this class. Does that make sense? My next class, I mean next Monday. Friday, we're just going to deal with our regular ANOVAs and factorial ANOVAs, potentially power, maybe something else. But for Monday, we'll get into repeated measures. Okay, so factorial ANOVA has this word in it, factorial, which is based off the word factor. So I want to talk about what factors are and what levels are. So can anyone tell me what factors are? There's a show on television, Fear Factor, where some people will talk about someone. They're like, oh yeah, they've got the it factor. But what is a factor? A factor is definitely related to an effect. It's not the effect, it's something else.
It's a component that leads to a level or a certain level.
It's a what that leads to a certain level?
Like part of the combination that leads to a certain level.
Part of the combination?
Like something.
Yeah,
What combination?
There are many factors that makes that it's a certain level. So a factor is just a
Okay, so you said there are many factors that lead to a certain level. Can you give me an example so I understand like what you're talking about?
So there is the factor of degree of freedom for the denominator and the denominator. So each of those are certain factors.
Okay, so that's actually true. So degrees of freedom, like when we've talked about these things before, we say that they're parameters. So the F distribution has these parameters that determine the shape of that particular H distribution. We can also say factors instead. F has certain factors, the degrees of freedom of the numerator, and the degrees of freedom of the denominator, that determines the shape of the F distribution that we'll be using to compare our observed F against. Okay, so can anyone give me like a non-statistical example? I want to check that that's on. I have this like creepy feeling that it's off. Okay, we're good. Okay, so what influences people's test scores?
It includes our mood,
Your mood,
our IQ,
your IQ,
background,
how much you studied,
gender.
whether you like the class or not, maybe your gender. All of those things are factors. So a factor, it's just another name for a variable. A factor is basically a variable that might affect some outcome. So you said level, but I want to reserve level to mean something else. So some outcome of interest. So test scores, that would be the outcome of interest. Does gender affect test scores, right? Does the factor gender affect test scores? So we have factors. What are levels?
How much is the effect?
No, it's not how big the effect of a factor is. So think about gender. If we just simplify, typically people talk about two, right?
Mm-hmm.
What are they?
Female.
Female and male. Those are two levels. So a level is basically just some specific value of a factor. So if we're talking about does studying affect test performance, you could talk about studying as the factor. You can talk about one level, people that study an hour or less. You can talk about another level, people that study between an hour and 2 hours. Another level could be 2 hours to 3 hours, right? Or you could break things down however you want. You could say people that study for the test less than 4 hours and people who study more than 4 hours, right? There's just different values that this factor could take on. So last class we talked about exposure to media on political support. So exposure to media was the factor, and political support was the outcome of the interest. So last class we had exposure to media, which was the factor. What were the levels for that? Yeah, so it had to do with the captions. So the level could be the caption was about an Israeli kid or about a Palestinian kid. That was in our first example. At the end of the class, we added one more, right? A control, where there was no caption, right? All right. So with a one-way ANOVA, I'm actually not so sure why they say one way, like what the historical meaning is behind one way. But basically, it's one factor. So last class, we were doing ANOVAs with one factor. That's it. So our one-way ANOVA has one factor and at least 2 levels, right? So with the 2 levels, it's sort of equivalent to the t-test, but we need at least 2. We can have 3, we can have 4, we can have 7, we can have 25. All right, so we have one factor, 2 levels. So last class we did 2 levels, Israeli-Palestinian, and then we had 3 levels, that should be Israeli-Palestinian and control. And the one-way ANOVA addressed the question, does this factor address some outcome? Or does this factor affect some outcome? Does exposure to media affect support for Hamas? Right? All right, so what if you had 2 or more factors? Well, that's Factorial ANOVA. So the Factorial ANOVA, we're dealing not with one factor, which we did in one-way ANOVA, but 2 or more factors. So, yeah. How can we make what?
Two factors in 2 levels.
So, 2 factors, 2 levels. So we talked about one factor yesterday, right? Exposure to media. And we said that we had, let's do just the 2-level version, right? So the Israeli versus Palestinian. So that's one factor with 2 levels. What else could potentially affect someone's support for Hamas? Where they live. So if they live in Gaza, they might support Hamas more than if they live in America, right? So you could look at exposure to media, Israeli versus Palestinian, and you could look at location, American versus Palestinian, right? But you could add more. Palestinian versus Israeli versus everyone else. Or like countries in the Middle East versus countries in Eastern Europe versus South America, however you want to break things up, right? So what you'd be looking for then is to see, well, I don't want to jump the gun. We'll talk about what we're looking for here. So this is going to address multiple questions. Before, when we had a one-way ANOVA, we addressed the question, does this factor affect that outcome? So what do you think the questions we're going to be addressing here would be?
Does this factor affect this outcome?
Does factor 1 affect this outcome? Does factor 2 affect this outcome?
Both.
Do both factors affect the outcome? Potentially we could see if one has a larger effect than another. True. There's one other thing. So the first 2 are the easy ones. Right? Do the factors affect some outcome? The second one is maybe not so obvious. Do the interactions of the factors affect some outcome? Now, to understand this, we need to talk about what interactions are. And we'll get to this in just a minute. This second question isn't so easy, so let's go through an example, but ANOVAs that we're going to talk about today and also on Monday all basically make the same assumptions. So what are the assumptions that the ANOVA is based off of?
Effect. The factors affect.
Those are the questions, but they're not the assumptions that we make. What assumptions does it make about the populations from which we're sampling? Did anyone do the homework? Yesterday's homework yet? You did, okay. Did you get 100 yet?
90.
90, okay, so hopefully you got this one right. So what assumptions is the one-way ANOVA based on? There are like 5 options, right? What assumptions did the t-test make? We can only use the t-distribution if we're sampling from normal populations, and we said the same thing here. So we need to be sampling from populations that we believe to be normally distributed. Or if we think they're not normally distributed, we can still do it anyway when we have a large enough sample size, right? And is equal to or greater than 30, yeah.
We assume that both variants are equal?
We assume that the variances are equal. So here we're going to be sampling from multiple populations, potentially, and we're going to assume that the variances for all of these populations are equal. Now there are ways to test this assumption. We're not going to talk about it in this class. When you take a graduate course in statistics, you may learn how to test this, this assumption. If you're really interested, you can come talk to me. But so we have the assumption also that the observations are independent, right? So we use random sampling. If we're making a manipulation, we do random assignment, right? So that way, my observation of her doesn't necessarily influence my observation of anyone else, right? So each observation that we're making is independent. And we're going to make a small exception to this next class. We're sampling from normally distributed populations with equal variance. This is described, if you've read like some of the study guide links, they may have mentioned homeoscedasticity. Homeoscedasticity, this big long word, means that the variances are equal. Homeo meaning same. All right, and also the sample sizes are the same for each combination of the different factors. So last class we had, what was it? We had Israeli, Palestinian, and control, and we had 3 observations in each, right? So for each group, we had the same sample size. Yeah.
But for t-test, we didn't have to make like sample size equal because in the independent test, you have N1 and 2.
Yeah, for the independent test, we didn't need the sample sizes to be equal. But for the paired t-test, we needed the sample sizes to be equal, right? Because we're taking different scores. And if you don't have equal sample sizes, there's nothing to take the difference between. So you need equal sample sizes for the dependent t-test. You don't need it for the independent t-test. And you just pool the variance, right?
So we also need this for the ANOVA.
You need, like the dependent t-test, yes, you need to have equal sample sizes. Okay. This is called a balanced design. There are equal number of people, or not necessarily people, but of observations in each group that you're looking at. Okay, so now let's talk about dependent and independent variables. What are dependent variables?
What we are observing, what we suppose.
They're variables that we're observing. Okay, but we can also observe independent variables, so just observation alone doesn't make the distinction clear.
I mean, it depends on location, something, it depends.
So we were talking earlier about like support for Hamas, and you said that the mean could depend on location, right? Now the mean is measuring support for Hamas. It's support for Hamas that's the dependent variable in that example. It's the variable that is thought to depend on something else. So it's the variables that are thought to depend on some factors. So the sum outcome in question, or the dependent variable in question, last class was support for Hamas. This class we're going to talk about humanity's self-esteem. So you guys know what self-esteem is? It's basically like how good you feel about yourself. There are different types of self-esteem. So there's just the regular or plain old self-esteem, but then there's also like ethnic group self-esteem. Like, how good do you feel about the particular ethnic group that you're from? Or gender self-esteem. How do you feel about the particular gender that you're from? Humanity self-esteem is basically like, how good do you like people? How good do you think humanity is? Right? Do you think positive things about humanity? We're good, we're making progress, we're making the world better? Or do you think like we're destroying everything and ruining everything? Okay, so we're going to talk about humanity self-esteem a little bit. Now, independent variables, what are these?
The factors that affect.
The factors that might affect. Now, when we talk about independent and dependent, like we're hoping that the independent variables affect the dependent variables, but we don't know if they do. This is why we have to do the statistics. But when we're talking about it, yeah, the independent variables are the variables that are thought to potentially affect the independent variables. These could be manipulated. They were manipulated last class when I showed people pictures with different captions. That was a manipulation. Not all independent variables might be manipulated. So what could a factor be that's not manipulated? Location. Location. I can't make you live somewhere. I mean, I guess I could, but that would be really hard to do and really unethical, right? You're from where you're from. You're from Diyarbakir, you're from Istanbul, I'm from America. Like, I can't assign you to be from Sweden. You're from where you are. So that's a variable that I could observe. I can observe where you're from. But it's not something that I'm manipulating. So the factors in question. Last class was exposure to media. This class we're going to have two of them. One is going to be sex. Another one is going to be experience with a natural disaster. Have you lived through an earthquake, a typhoon, a hurricane, a tornado? Have you experienced a natural disaster? All right, so what are the levels for our factors going to be? They're the levels for our independent variables. So we have sex.
Male.
We're going to just stick male and female, okay? How about disaster?
Not being encountered disaster or being encountered from disaster to disaster.
Yeah, we could do something like the number of disasters that you've encountered. So 0, 1, 2, 3, 4. I'm going to make it simpler than that. I'm just going to say
If you had
some or none. So you've had experience with the disaster or not. Yes or no? Okay, now the questions. Does humanity self-esteem depend on sex? This is related to our first factor. Right? So humanity self-esteem could be related to sex. The stereotype is that women are more caring and more nurturing. Maybe they have higher humanity self-esteem. Maybe. I don't know. So, this is, if we rephrase it, we're asking, is there an effect of sex on humanity self-esteem? Does humanity self-esteem depend on disaster? Is there an effect of experiencing a disaster on humanity self-esteem? Could it?
could.
So you go, no, how could it?
Like if I had that experience and I would change my perspective toward like all things like find me why I would like for example some people didn't help me and I see didn't help me so I do not like them. So
Yeah, so potentially if there's a disaster, if you're fighting for yourself and everyone else is fighting for themselves, you could be like, man, this is a dog-eat-dog world. People aren't very nice. They're really screwed up. Your humanity self-esteem can go down. After the Von earthquake, I first started to think about humanity self-esteem and disasters. I think this is an interesting question, and potentially we can do some research here if anyone is interested. Anyway, I thought it might be the opposite. So what happened after the earthquake in Von? People appreciate their lives, but what else happens? Do people like fight? Most of the time, people are helping each other, and support from other countries came in. So lots of other countries came in to give the people in Von assistance and help. Medical care, food, supplies, clothing, right? All that stuff. So you see all these people helping one another out. Maybe feel better about humanity, right? It could go either way. I have no idea. I haven't done the research. These are main effects. This is the effect of some factor, effect, or dependent variable. That's a main effect. Okay? Those are both main effects. The other question is, does humanity's self-esteem depend on the interaction between sex and disaster? Is there an interaction between sex and disaster in humanity's self-esteem? This is an interaction, and I said we were going to talk about an interaction, but we haven't yet. So, what is an interaction?
The relationship.
Okay?
The two factors being like divided together or some ratio.
The two factors being divided together, a ratio.
Related.
It has to do with the factors and how they're related.
Correlation.
Well, there shouldn't be a correlation because the way we're doing it, we're breaking things up into independent pieces, which by definition would mean that there's zero correlation. The only way we would have a correlation is if we had an unbalanced design. That would introduce a correlation, which is why we should use balanced designs and have equal numbers of observations for each group that we're looking at. An interaction is when the effect of a variable, or the effect... Alright, so an interaction is when the effect of a variable in the interaction depends on the level of the other variables that are in the interaction. Now, that's a mouthful. When the effect of one variable depends on something else, on another variable. So, let's use a very stereotypical example to hopefully make this clear. Please forgive me for stereotyping. Okay, so our independent variable is going to be the time spent talking. How much do people talk? And our dependent variables will be sex and the topic of conversation. So what levels are there for sex?
Female.
We'll do female and male. Okay, well, what could we do for the topic of conversation?
How long they talk?
No, how long they talk, that's the independent variable. Shopping. So one level for the topic of conversation could be shopping. Okay? Football. School. Family. Health problems.
Lots of things.
You could, yeah, potentially have lots and lots of things. Now, the main effects. What main effects would we be looking for?
Does sex affect partner?
Does sex affect the time talking? Right? Is there an effect of sex on how much time people spend talking?
Shouldn't that be the other way around? I mean, the dependent variable should be sex and topic of conversation. Independent, I mean...
Yes, you are absolutely right. Good grief.
Makes no sense.
Well, it makes more sense because that's actually correct. Extra credit. Yeah. Okay, so the main effects. One is potentially, does sex influence time spent talking? So what's the stereotype?
Females are talking too much.
Well, I wasn't going to say too much, but that females talk more, right? So we would expect a main effect of sex. So women talk more than men. And topics. There could be a main effect of topics, right? Some topics people talk about a lot. Other topics people talk about a little. So things that people talk about a lot are things like their family, their school, things that people don't talk about much, at least in America, are things like how much money they make, or how much money their family makes. Is that the same here? Do people talk about how much they make here? Like openly, like, oh yeah, hey, I just got a raise for this much, and I'm making that. It's kind of private, right? Don't talk much about that. So we'd expect that some topics are talked about more than others. Now, the interaction between sex and topic. Basically, we're looking to see if the effect of sex depends on the topic. Or or does the effective topic depend on sex? Okay? So, if we rephrase it differently, do women talk the same amount more than men for every topic? Now, I said same amount because, like, we already know that just by taking a random sample, we probably are never going to get exactly the same amount. So we need to use statistics to figure out if they are statistically insignificant, meaning the same, or statistically significant, meaning they're different, right? So, what do you think? Do women talk the same amount more than men for every topic?
No.
No. What's the stereotype?
For example, for football.
For football?
Men talk more than.
Men are talking more. Whoa, bring them up. Did you see that Messi guy and he was playing with Pele and they were kicking? I don't talk about sports. Okay, so the idea is that men talk more about sports, right? And what do women talk more about?
Shopping.
Shopping! Hey, did you see these new Gucci shoes that I got? Oh. So, if they talk the same amount, statistically there's no interaction. If they don't, there's an interaction. So stereotypically men talk more about sports, even though women talk more sort of overall. This means that there's an interaction. So the effect of women is just, they're talking more than men, right? But this effect, talking more than men, actually depends on the topic of conversation. It's not always the same amount for different topics. For some topics, it flips. That's the interaction. Does someone have a question?
Is it affects our results, statistics results?
Well, what we're going to do with the Factorial ANOVA, we're going to look to see if each of the factors has an effect. That is, are there a main effect of the different factors? And then also we're going to look at whether there are interactions between the factors. If the effect of one of the factors depends on the level of the other factor. Alright? Okay. So, how do you spot interactions? So here's a line graph. Is there an interaction or not?
Yes.
How do you know?
Which one? Male or female?
SOA is stimulus onset of synchrony, but you don't even need to know what these axes represent in order to determine
I
if
think
there's an
that's
interaction.
because whether it's going, like one of them is increasing, one of them decreasing, so there is point.
So, like, one of them is sort of going up, and the other one is going down, right? So, the lines aren't parallel. So, an easy way to spot an interaction in a line graph is to look for non-parallel lines. Now, if you look at just the first two data points, well, that looks pretty parallel. And these, well, they're a little different. They might not be significantly different. But overall, these are tending to sort of sweep up, go down and up, and these are sort of coming down, right? The lines aren't parallel. How about in this? If you were looking at a bar graph, how can you tell? But we don't have lines here.
But we can compare. Can we compare?
Yes, you can compare.
So, for both of them, for verbal, pictorial is less than verbal.
Okay, so pictorial overall seems to be less than verbal. Would that be an interaction?
For both? No.
That would be an effect of the Q type, right? So that these are smaller on average than this could be a main effect of Q type. All right, so what's the interaction? There is an interaction. What is it? So we have, in verbal and pictorial, we have these black bars and these white bars, right?
Differences between verbal and pictorial about these two.
Yeah, so the differences between the bars. So here we have a tiny difference between these bars, whatever they represent. And here we have a large difference between the bars. So basically, the gap in one is a lot bigger than the gap in another. The gaps aren't the same size. I actually really don't like bar graphs. I prefer line graphs. And sometimes when I get a bar graph, I will draw lines. And I will try to figure out, are those parallel or not? No. Doesn't look so. So you can sort of easily spot an interaction by looking for lines that aren't parallel or for gaps of different sizes. Now, you don't just want to look at some graph and say there's an interaction there, because these differences may not be significant, which is why we need the statistics in a different. So we should be careful. Yeah?
So for the first one, is it parallel?
No.
So the first one, these aren't parallel. If they were parallel, like they'd both be going like this, or imagine that we have the top one that goes like this, the bottom one would also sort of go like that, right? So there'd be like sort of constant difference between the two.
If,
right?
if there is a parallel, does it mean interaction?
If they're parallel, it means there's no interaction. So when you see something that doesn't look parallel, the big question is it not parallel enough? And you need the statistics to be able to answer that. Okay, so back to our questions. Does sex experience or the interaction between sex and experience affect humanity's self-esteem? Before we get to the second part, I just want to make sure everyone understands interactions. Okay, so does anyone want to try to state the null hypothesis? Yeah.
First, levels of sex, they are equal. This null hypothesis that male, the effect of male and female, they are equal.
So the mean for male equals the mean for female, okay?
And the mean for yes and mean for no, they are also equal.
Mean for yes and mean for no are equal, okay?
And there's no relation between the sex and the experience.
There's no relation between the sex and experience, no difference. So if we wanted to state this with all of the means, we'd have something like this. The mean of males equals the mean of females equals the mean of disaster equals the mean of no disaster equals the mean of males in a disaster equals the mean of males not in a disaster equals the mean of females in a disaster equals the mean of females not in a disaster. Oh, good. So this could very quickly get very complicated. Imagine that we had another factor involved. So we would have to include all of the levels of that factor, and then all of the potential interactions with all of the potential levels of the other factors, right? So this could get really long. So an easier way to do this is just all means are equal. What's the alternative hypothesis?
All means are not equal.
All means are not equal. Or not all means are equal. What is it? Alright, so to do our F tests, part of it depends on getting the sums and squares, right? We get sums and squares, then we're going to get the degrees of freedom, then we're going to get our mean squares, and then we're going to do our F tests. So let's talk about the sums and squares. Now I put up the old because this is basically the same way you did things last time. So how do you get the sum and squares total?
Unbiased variance?
It's not the unbiased variance, it's the numerator of the unbiased variance.
Effect freedom.
Divided by the degrees of freedom.
Effect of mean of x.
Okay, hold on. Well, was it you who was talking?
Mean of squared effects, mean of squares, and
So mean squares effect over mean squares, I'm sorry, F versus mean squared error. But that's not the sum of squares. What is this? This is F. That's F. Okay, let's move to whoever it was.
Unbiased variance.
Okay?
By degrees of freedom.
unbiased variance divided by the degrees of freedom. So the unbiased variance is this over degrees of freedom, and then we're going to divide all of that by degrees of freedom? No. This is the unbiased variance, and part of the unbiased variance is what we're looking for.
This is the first denominator.
Yes, the numerator.
Yes.
Yes.
This is the numerator.
Yes, that's what.
So, the sum of the squares total, yes.
Here the mean is the total mean.
That's right. We're going to take the difference between every score that we have and the grand mean. Okay? So we're going to get every difference between every score and the grand mean, square those puppies, add them up, and that's our sum of squares total. That's exactly what we did for the last class. Exactly the same thing, right? Okay, so how did we get the sum of squares for our factor in last class? So before I just said sum of squares effect, right? These are both sum of the squares for different effects, so I'm actually going to name the effects. So sex, disaster. Yeah?
Wait, shouldn't we do it like each by each, like because I mean, sex we have two levels. We have different effects. We have different errors.
We have different effects, different errors.
Yes.
Actually, since we have a balanced design, and we only have two levels, the effects are going to be opposite of one another. One will be positive some number, the other one will be negative one number. If we had three, we could have different effects for each level potentially.
We can combine them.
Okay?
You mean that we can combine them? Like,
Add
is it
them.
possible to add?
Yeah, how did we do this for last class?
Variance, we add variance. I don't know.
The variance for the effect, we just
Add
the
them.
total of it.
Yes,
just
so
sum
we-
the total of it.
Subtract mean, central minus mean grand.
So we subtracted the grand mean from like that sample mean,
Yes.
from that particular like group.
Yes.
Right? So what we would want to do is subtract the grand mean from the mean of males. Right?
Mean of
And also square that. And we're going to get the mean of the females minus the grand mean. Square that, right? Now, remember when we did it in class, I didn't just do this one and that was it. I said for each observation we had in that group, we added that. So basically, if you think of n as being the sample size for a specific condition or a specific group, so here for sex, like the number of all of the males, right? Which is going to be equal to the number of all of the females because the design is balanced. So what we can do is multiply the square difference from each, multiply those both by the number of males and the number of females that we have.
why we have all?
So last class, let me go back. So we had this, right? We said, okay, the Israeli mean, basically we have that mean in for each observation in here, right? We have that mean plus some error, right? So we had 8, 8, 8, we had 12, 12, 12. Subtract the grand mean from both of those, we had -2, -2, -2. We had 2, 2, 2. We squared those, 4, 4, blah, right? So here I just added them all up, right? Now if you notice, there's a pattern here. If we call this n, right? We have 3, Palestinian. So we can rewrite this as -2 squared plus 2 squared, all of this times 3, right? Okay, so we're going to find the square difference between the means for each level of sex. What's the mean of the females? What's the mean of the males? Get the difference between those means and the grand mean. Square those things, sum them up, and multiply by the number of individuals of each sex. So if we had like 4 males and 4 females, we wouldn't multiply by 8. We would multiply by 4. We have 4 of each. All right. This is what I mean by the number of observations contributing to each mean. We have 4 males. We have 4 males that are contributing to the mean of the males. Yeah?
And why do they do it this way? It doesn't make it easier just for calculations, or just because makes it good?
Because saying this is a lot easier than saying find the square difference between the mean of males for the first male minus the grand mean plus the mean of the males for the second male, right? It's basically, it is the same thing. Algebraic, it's just an algebraic manipulation. All right. So the sum of squares for the disaster. It's going to be exactly the same, except we're going to change this to each level of disaster. So we find the mean for the people that have been in a disaster, subtract the grand mean from that, square it, add it to the squared difference between the mean of the people who haven't been in the disaster and the grand mean, and then multiply that by the number, by that n, I guess you could say half of the total. If you consider all of the observations, then half of them are in one and half of them are in the other, but right. Okay. Ruby. So that's O. That's easy. So the sum of squares, the sort of new. The sum of squares for error. This is very similar to what we did last class. It just has a slight change. How did we get this for the last class? Yeah?
We subtract the grand mean from the mean of male and females. No, we separated each individual error from both the female or male.
Okay, we will subtract from total the effect one that we got there.
I'm going to go back to the slides from last class after I change the video.
The individual score minus sample mean.
Individual score minus the sample mean.
Yes.
Square.
Yes! Square that. Add them all up. So not the grand mean, but the mean of the individual sample that we were talking about. So let's go back to the other one just to make it clear for anyone who isn't completely on board. So the error variance is the variance of the observations around their sample means, right? So 7 minus 8, this is the sample mean for this group, right? So that was -1, this was 0 and 1, and this was 1, 0, and -1. When we squared those, we added all of those together, right? Okay, so that was the error variance when we had one factor. How about when we have 2?
We will subtract again, but for both of them. So will we find 2 sample means?
What will we do? That's a good question.
You mean we should combine both errors for both factors?
Yeah. Why?
I'm saying we want the overall error.
So we should.
Now the error is calculated based on your best guess, your best estimate of what the person should be versus what they actually are.
So we
Yes.
can actually make that. We can just combine the mean of males, females, yes, no, and just find the error.
So all we need to do, so we have males and females and we have yes, no, right? Previously we found the mean for males, we found the mean for females, we found the mean for yes, we found the mean for no. But we could also split this up a different way. We could get the mean of males yes, and the mean of males no, and the mean of females yes, and the mean of females no, right? Now, for any individual person, our best guess about how they scored would be if we knew their gender. She's a female. Are you from Palestine? No. Or wait, what were we talking about here? And have you experienced a disaster? So she has experienced a disaster. So we would look at the female disaster group, and we'd say, okay, our best estimate of what she is based on this. And then we want to see how far she is from that estimate. That's our error, because she's different. She grew up in a family that made so much money. She grew up in a family that had so many kids. She experienced a specific type of education. She had all of these other things that could potentially influence the results are the error. So we're going to sum up all the square differences between each observation and the conditioning. The condition. So what's a condition? So a condition is one combination of the factors. So that's what we just did, right? We took a combination. This was not an ordered combination or a permutation. This was just a combination. Okay, we don't need to talk about that. Right? Male, yes. Male, no. Female, yes. Female, no. If instead of doing yes, no, we said 1, 2, or 0, 1, or 2 or more, then we would have female 0, female 1, female 2 or more. Male 0, male 1, male 2 or more. Right? Is that a sigh of like, I got it? Or is that a like, oh?
It sounded good.
Yes. Basically, we're just combining the different levels from the different factors.
Yes.
We have one level of one factor for each of the levels of the other. That's all it is. All right. So, for example, if we had one of the observations in the female and disaster group was 10, and the mean of the female and disaster group was 12, so the difference would be -2, and the square difference would be 4. Let me make sure that I'm reading this right. Okay, so one of the observations that we have, so one observation is 10, but the mean for that condition was 12. So it's the difference between that observation versus the mean of the condition that observation is called. Okay?
How can we calculate the mean of female and disaster? So we have to make 4 calculations, 4 new calculations.
Yes.
How do you calculate mean of female and disaster? So like you would have something like, okay, so you have female disaster, female not, male disaster, male not, and you have 1, 2, 3, and 4, 5, 6, and 2, 8, 3, 9, versus pi e not I, 2, okay? So then you just add those things up and get the mean, right? So this is 2, this is 5, this...
No, it's not the question.
Because
That's not the question.
first we have only mean of females only, males only, no only, and yes only.
How do we get the mean of the females?
Female and disaster.
We got females, males. No.
But how do we get the mean of the females? So, like the data that you would get would be something like this.
Yes.
You have a group of females that have experienced a disaster, their scores are this. You have these other groups as well, and their scores are whatever they are. So how do you get the mean of females?
Just combine them together.
Just combine it, right. So the mean of females, so if we want to do something new, females is we have 1, 2, 3, 4, 5, 6. Get the mean of that. The mean of the males, so males would be 2, 8, 9, I, E, 2. Get the mean of that. Right? And if we wanted to do the mean of the disaster, so disaster would be 1, 2, 3, that's from here.
2, 8.
And also from here, 2, 8, 9. If we wanted to get the mean of no disaster, well that's this and this. So 4, 5, 6, and pi e 2. Right? So calculating the means, you just need to group the appropriate information together. So we want to get the means of the females, we look at all of the females. We want to look at the mean for no disaster, we look at all the individuals from no disaster. Yeah.
Can we give the mean after calculating the females only, and if that's the only, is this a specific calculation that we can combine those means together? After we got the female.
So if you took the mean of female and averaged it with the mean of disaster, is that what you're saying?
Then give us the, no?
That will probably, I haven't thought about this question. I'm going to say the only time that you will get those two things to be equal is when there is not an interaction. Actually, I'm not really even comfortable saying that. I would need to think about that more. But yeah, you calculate. I mean, you just get the mean of this, and the mean of that, and the mean of this, and the mean of this. So yeah, I guess we could do it. Okay, so 1, 2, 3, 4, 5, 6. So what is the mean? So is that 3.5? Halfway between here, halfway between here, halfway between here. And 1, 2, 3, 2, 8, 9. I'm going to use ours.
No, that's
Mean C. 1, 2, 3, 2, 8, 9. There we go. So that, actually, let me assign that to MD. That will be mean disaster equals, actually, home, where's home? Equals. And our mean for females was, this should not turn out to be the same as the mean for both of them. So C, and it was 1, 2, 3, 4, 5, 6, right?
yes, 3.5.
So mean D, mean females, and we can get the mean of the means.
So that is 2, female and disaster.
Mean C, mean D, mean F. This will give us the mean of the females and disasters. That equals 3.8333. And the mean of females and disasters is 2.
So it's not.
So it's not.
We should find the mutual observations of both, and that's how we combine.
We should find the one.
One of both mutual, like 1, 2, 3, in both.
It depends on what you want to find. If you want to find the sum of the squares for the error, you need to be comparing 1 to 2, and 2 to 2, and 3 to 2. You need to be comparing 4 to 4, and 5 to 4, and 6 to 4, right? Subtracting the mean of that condition from each observation in that condition, squaring those, summing those, right?
And you said FD, we got it from F and D just by combining the 1, 2, 3, which are the common observations. The common.
No.
How do we find 1 through P? If we have females?
I told you that's what the data were. We started with this, right? We said these are the data that you have. You had your female disaster group, the data were this. We had this group, the data were that. I gave you that. Then I thought the question was, well, how do you compute the mean for females? And I just said you add up all of the females and take that mean.
So what if it was the other way around? What if we have females, males, no, yes, and we want to have the interaction? Male.
Unless you have information about how to get those pieces out, you're not going to be able to do it. I won't give you information like, okay, here are all of the data. Now what's the mean of the females? Like I will say, maybe here are all of the data, and here is an indicator of which one is male and female, and here's an indicator of which one comes from disaster and not. And then with that information, you'll be able to figure out what your different groups are. I'm not just going to say like, here's the data from the females and here's the data from the disasters. Which females were in the disaster? Right? You could do it, but you're making it more complex than it needs to be. And it's already complex enough, I think.
Yes.
I'm a bit scared because I think we're not even halfway through this. And this is the easy stuff. This is the old stuff.
Easy?
Yeah.
Really?
This is sort of new.
It's complicated.
We'll just wait until the next slide. All right. So, the new. We want to get the sum of squares for the interaction. How are we going to do this? Well, let's talk again about what each score contains. So what does each score contain? Each score contains the grand mean, but the sample mean also contains the grand mean. So that would be like saying we have the grand mean and then the grand mean again and something else. So let's not talk about it in terms of the other means, but let's talk about the grand mean and the effects.
The effect.
So what? Each score contains the grand mean,
The effect of level or something?
effect of,
Each level. Like male, female.
we just say the effect of sex,
Okay.
Effect of disaster?
right? And the effect of sex depends on what level it is, but basically it's the effect of sex, right? So it's going to be a grand mean, the effect of sex,
Effect of disaster.
The effect of disaster.
effect of disaster,
And the error
error,
Of total?
Should we do that? Because it's individual.
not the total. The error is not the total. The error is part of the total.
I mean error in general, because there is no different error for sex and disaster.
Right, you just have error. We're missing one.
Variance.
What are we missing? That's what I want.
The interaction between
Side
effects.
effects?
The interaction. Yeah. So the grand mean, effect of some level, sex, effect of some level, disaster, the effect of the interaction, error. If we want to just get the effect of the interaction, what do? So before, yeah, we were doing subtracting, right? We're subtracting to get rid of the effects of the grand mean. And we're subtracting to get rid of error and other things. So what do? So each grand mean contains the grand mean. That's it. Each of the means in the interaction contains the grand mean and the effect of what?
First and second.
Of the first factor and the second factor and the interaction. So the means basically collapses over the error. So when you got the mean, you aren't including the error. Okay, so we have each grand mean with the grand mean and each of the means in the interaction or the mean for each condition has those parts. So what would be left if we subtracted the grand mean from each of the means in the interaction? subtracted the grand mean from them, what would we have? I mean, that's what we were doing earlier. So, like, each of the mean for sex, right? So the means for sex, what do the means for sex include? The grand mean and the effective sex. Right? So when we subtracted the grand mean from the mean of sex, we got rid of this and we were left with that. So if we subtract this from this, what will we be left with?
Effects of interactions.
Interaction, effects of disaster, effects of...
Yeah, so if we subtract these from this, we will only get rid of that. Right? Now what we're looking for is this.
We subtract the values.
What do we subtract?
Interaction of sex and interaction of disaster. What? No, we will subtract effects.
From effective sex and effective disaster.
So we need to subtract out also the effect of sex and the effect of disaster, right? Good. How can we do that?
We found the effect.
Do we find the mean for those four?
Okay, now let's think about it. If we took the mean for the sex, the mean for the sex is the effect of the sex and the grand mean. So if we already subtracted out the grand mean, and then we subtracted out the mean for the levels of sex, we would get rid of this, but now we're at -1 of those, right? And we can do that again with this one. So let's subtract out the mean of disaster, which will get rid of the effect of disaster, but it will also get rid of another grand mean. So that will leave us with -2 grand means in this. So how do we get back?
Plus 2.
We can add 2 grand means back in and be left with that. That's the hard way to do it. So this is what you guys came up with, and this is actually the hard way to do it. So you take the mean for each of the levels of the interaction, basically the mean for each condition, subtract the mean of the corresponding level of sex, which will get rid of the effect of sex and the grand mean, subtract the mean of the corresponding level of disaster, which will get rid of the effect of disaster and the grand mean, but now we just got rid of the grand mean twice, and we only had 1 in there. So here, we just needed to add the grand mean in back 1. Why didn't we add it back in twice? Well, because when you guys came up with that earlier solution, the first thing you took out was the grand mean, whereas here, I didn't take that out first. Then you square those differences, multiply by the number of observations in each condition, you're good to go. The easy solution, like variance, independent sums of squares add up, right? We said sum of squares total equals sum of squares effect, that's the sum of squares error. So, you can read that. But basically what we can do is we can get the difference between each condition mean and the grand mean. Difference between each condition mean and the grand mean. That will leave us with the effect of the interaction, the effect of sex, and the effect of disaster. Now, the sum of squares, sex, that's the effect of sex, right? When we want to find the sum of squares for the effect, right? So that sum of squares that we just did that first part, it contains the sum of squares for sex. It also contains the sum of squares for disaster. So all we need to do then is just subtract out those sums of squares, and we're left with the answer that we're looking for. So the sum of the squares are interactions, or I'm going to say the sum of squares for sex dis, meaning the interaction, the combination of those factors. Okay, so let's generalize for interactions. Okay, so we're going to sum up the square differences between the means of each combination of the factors involved in the interaction and the grand mean, and multiply the sum by the number of observations contributing to each mean within the interaction. Then we're going to subtract the sums of squares for the main effects involved in the interaction. We're also going to subtract the sums of squares for lower order interactions. Let's do an example. So imagine that we didn't just do sex and disaster. We want to look at sex, disaster, and married. Maybe, being married changes your perspective on humanity's self-esteem. You're married to a good person, and you're like, oh man, people are great, humanity's great. You're married to someone like your mother-in-law, and you're like, oh man, this is horrible. No offense, mom-in-law. Anyway, so the sum of squares for this three-way interaction, there are three things here, right? Three. So how do we do it? Well, this is the number in each particular group: male, disaster, not married. So the number that we have there. So times the difference between each combination of those factors, the mean for that. So this is the mean of males, disaster, married, minus the grand mean squared, plus the mean of the females in the disaster who are married, minus the grand mean squared, plus the mean of the males not in the disaster that are married, minus the grand mean, plus through the rest of it.
It goes 9 ways.
Goes 9 ways.
Because the MDY.
You said it's 9 different combinations.
Yeah, there's a
Male, disaster, married, that's yes. I didn't want to use M twice.
yeah. So there's different 9 different combinations.
How many combinations do we have? Do we have 9?
No, it's
Because we have 4 for sex and disaster, so we have 9 for sex and disaster.
So we have 4 for sex and disaster. So we have male disaster, male not, female disaster, and female not.
So we have 9.
We don't have 9. We have
Johnson.
not 27.
8.
8. We have 2. We have 2 levels of sex times 2 levels of disaster times
Mary.
married or not married, 2. It's 2 to the third, right? Which is 8. So let's write F, G, F. And we have married, yes, 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 yes,
No.
and no, 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 no. Okay? So for each of these groups, we would subtract the grand mean from it. This is where I get really frustrated if we didn't start on time. Okay, so that's that first part that I said. Then we need to subtract out the sums of squares for the effects. So that's minus the sum of squares for sex, which we know how to calculate, minus the sum of squares for disaster, which we also know how to calculate, minus the sum of squares for married, which we also know how to calculate. Now, the other part of this was that we also need to subtract the sums of squares for lower order interactions, because this is also going to contain, or not this, but like the means of our different groups. They're not just containing the grand mean and the effect of the sex and the effect of disaster and the effect of marriage. They're also containing the effects of the lower level interactions. So we also need to get rid of those. So our lower level interactions, we only have 3. We can have an interaction between sex and disaster, an interaction between sex and married, and an interaction between disaster and married. Right? So we're getting rid of, notice this has 3 terms in it, these have 2 terms in it. These are the lower order interactions involving these same factors. Okay? So that's it. That's how we get our sum of squares. Alright, so now what we're going to do degrees of freedom. Let's fly through this. So degrees of freedom total. This is really easy. This is n times the number of conditions minus 1. I'll let you guys go through the math on your own. Basically what this is the same thing as the total number of observations that you have minus 1. So it's the same thing that we had before. You have n number of people in each of the different conditions. So n times that number of conditions will give you the total number of observations that you have. Now here I have this 2 by 2 to figure out how many factors you right? Or how many conditions you have. This is typically a way that factorial designs are described. So people will say, I did a factorial 2 by 3 by 6 ANOVA, meaning that you had 3 factors. One had 2 levels, one had 3 levels, and one had 6 levels, if I'm remembering what I said correctly. Okay, so that's easy. Degrees of freedom for sex, degrees of freedom for disaster. What's this? This is also easy.
No, minus 3. Minus 2 levels.
We have 2 levels of sex, so how many degrees of freedom do we have? 1, that's right. Number of levels of sex minus 1. How about the degrees of freedom for disaster? Same thing here. Okay, the sort of new. The degrees of freedom for the error, how many do we have?
Total minus.
Total minus.
Group.
Total minus the number of groups that we have. N times conditions, well that's the total. Minus the number of conditions that we have. That's the number of groups that she was referring to. That's exactly right. Yay! Those are just different ways of calculating it. You can use whatever you prefer. Okay, now, degrees of freedom. The old easy way to do this, remember degrees of freedom, just like the sums of squares, they add up. So if you know the degrees of freedom for the total, and you know the degrees of freedom for the main effects, then you can figure out, if you just have a simple 2 by 2 like this, what the degrees of freedom are for the interaction. The easier new way is you just are going to multiply the degrees of freedom for each of the factors involved in the interaction together. So we have 1 degree of freedom for sex, times 1 degree of freedom for disaster. 1 times 1 is 1. We have 1 degree of freedom for the interaction. Now let's make this make a little bit more sense. So imagine that I was comparing males and females of different years in college. Freshman, sophomore, junior, senior. On some measure. I don't know what the measure is, but here are the means that I got. These are the means for the freshman, sophomore, junior, senior. We have the means for females, males, and also the grand mean right there. Now, we can set this to anything that we want it to be. Anything in the world. Pick a number. Alright, I picked a number 7. If this is 7, and the mean is 10, what does this have to be? 13. That's exactly right. So that one wasn't free to vary. Right? I could pick anything I want for this. So I picked 24. You need to have -2 to balance that out. That one wasn't free to vary once I set that. The junior also, I could put anything I wanted to. 13. So what does this have to be? This one also has to be 13. So that's set. Are these, can I pick anything I want for this? No, I can't because this is already set. So if I know these 3 and I know this, that one is already set. It's 8. And the other one is also set. So we had a 2 by 3, right? 2 levels of one, 3 of the other. We have 1 degree of freedom for the one, we have 3 degrees of freedom for the other. Right? Not sure if I said that right. We have not a 2 by 3, a 2 by 4. This is 4. 2 by 4. 1 degree of freedom for the one, 3 degrees of freedom for the other. There should be 3 degrees of freedom for the interaction, and that's exactly what we just found out. Okay, so mean squares, you guys know how to do this. F, you also know how to do that. You just divide the mean squares for the effect or the interaction that you're interested in, and divide that by the mean squares for the error. And there's only 1 mean square for the error here, so you just use the same denominator, and then make sure that you calculate for the critical values and the p-values using the appropriate degrees of freedom from the F distribution. You guys can read through this. Basically, I'm saying that the effects and interactions are independent of one another, and you can observe any combination of effects and interactions. All right, that's it.